Okay, everyone, I'm going to go through this part, which is on the energetics. So if you're looking at your notes, we are looking at this chapter. Just let me scroll back. So we're looking at chemical energetics, and I'll be going straight away to look at some of the methods to calculate enthalpy change. So I'm skipping some of this first to do a recap later because those are experiment, and we are looking at how this part from this section onwards, how do we calculate the enthalpy change? All right, so to summarize, there are a few methods to determine enthalpy change. One will be using Bond energy. Another uses Hess's law cycle or algebraic method. And another one uses delta HC value and delta HF value. Okay, so I'll be covering until the HCHF value part. All right, so for a start, what is enthalpy change? Enthalpy change is usually the change that happens during a reaction, and there's an energy change. So if we look at the reaction, if you remember, there are exothermic and endothermic reaction. So if this axis is energy, and this is progress of reaction, if we have an exothermic reaction, our reactant actually is having higher energy than our product. So our reactant containing more energy than our product. So there's a net amount of energy that has to be given out, and they'll be given out as heat. So the enthalpy change over here is negative. So this is an exothermic reaction. So in an endothermic reaction, this is our energy, and this is our time, progress of reaction. And if it's an endothermic reaction, our product is having higher energy than our reactant. And where do this energy come from? It has to be supplied into the reaction. So the reaction gains heat energy to have greater energy, and therefore the product ends up with higher energy than the reactant. So this type of reaction, we call it an endothermic reaction, where heat is taken in from the surroundings, right? So basically, we can see that delta H seems to be like the energy difference between a product and the reactant after the reaction is over, right? So the enthalpy change, which is the delta H, it is actually the energy change during the reaction of the system is having. Okay, the energy changes in the system after a reaction. So there are many ways to find the energy changes in the system after a reaction. There are a few methods, but whichever method that we're using, the main basis of most of the method is based on this thing called Hess's law. So Hess's law states that it's a form of a conservation of energy. So it states that as long as the starting and the ending is the same, so the energy changes in the reaction is regardless of the pathway. So the energy change is going to be the same, whether the same reaction is carried out in one step or the same reaction is carried out through many steps. So let's fix this as a starting point, and we fix this as the ending point. So this is the start, this is our reactant, and this is our product. So whether if we go through a direct path like this, which the energy change is delta H1, or we go, let's call it delta H3, 2. Or it goes through another pathway whereby it first changes to B and then B changes to D. Okay. Whether it goes by this pathway, or this pathway, the energy change should be the same, because it states that enthalpy change is the same whether the change is brought about in one or many steps, right? So if we call this, if this is the first pathway is sum of delta H1 plus H2, then this pathway is delta H3 plus H4, and if we call this H5, then we can say that H1 plus H2 equals to H5. H3 plus H4 equals to H5, right? So the enthalpy change of a reaction is only dependent on the starting reactants and the ending reactants. So it's independent on the pathway. So we can calculate the enthalpy change using many different ways that we are going to look at. The few common ways to calculate enthalpy change that we're going to look at is, firstly, we use bond energy to calculate energy change. So during a reaction, bonds are broken, bonds are formed. So we find out what is the change in the energy required to break the bonds, energy given out when bonds are formed, then we will know what's the net energy change in the reaction. So if we're using bond energy, then we will be using values in table 12 of the data booklet. And the formula that we'll be using is delta H reaction equals to bond energy of reactants minus bond energy of products. Okay, so that is first method using bond energy. So you can see is table 12. We will use table 12. Let me show you table 12. Okay, table 12 is this bond energy. Okay, so we'll be using bond energy in the calculation if we are using bond energy method. Okay, so what other methods besides bond energy method? Besides bond energy method, if you want to calculate delta H of a reaction, we can also use delta HF values. These delta HF values can be seen in table 13 of the data booklet. So if you go to the table 13 of the data booklet, you will see all these values here, which are delta HF. So you can make use of delta HF values to calculate the enthalpy change of a reaction. So we are using the values. And how do we make use of the values? We will make use of this formula. Delta H reaction is equals to sum of the delta HF of the products minus sum of the delta HF of the reactant. Okay, so we will use the HF values to calculate. That is another way. The third way, if you do not want to use bond energy, not using HF, we can use something called delta HC values to calculate. Delta HC values can be found in table 14 of the data booklet. So it looks like this. So this is table 14 and you have all the delta HC values. So you're taking these values to help you in the calculation, and the formula to calculate a delta H of a reaction using HC values will be sum of HC of reactants minus sum of delta HC of product. Okay, so I stop here first for these three methods. Bond energy, delta HF, delta HC. So all the values are found in the data booklet, table 12, 13, 14. Okay, so these are the three ways. Now, how do this formula come about, whether it is the first one, reactant minus product, or the second one, product minus reactant, or the combustion one, reactant minus product? How do this formula comes about? It comes about from drawing something like this, which we call the Hess-Law cycle. That means besides using formula methods to calculate, besides using all this mathematical formula to calculate, we can also find out enthalpy change of a reaction by drawing Hess's law cycle. Okay, but if there's a choice, we do not spend our time drawing the cycle, but the cycle is the basis of all the mathematical formula. So Hess's law cycle can be drawn, and through using the cycle, you can also solve the question. Besides using Hess's law cycle, if you don't want to draw a cycle, there's another way that you can get the enthalpy change of a reaction if you are given equations like this. Look at this example here. You are given many equations. So if you are given many equations, what we can do, we can manipulate the equations. So we can manipulate the chemical equations, and that's another method that we can use to calculate delta H. So there are 5 methods here that we can learn how to allow us to calculate delta H. And of course, each method, sometimes they will tell you to refer to the data booklet. Some methods have additional requirements, like for bond energy and so on. Okay, so generally, these are the 5 methods to allow us to calculate delta H if it's non-experimental. These are non-experimental. That means you're not collecting data, not doing experiment, but you're just using some data booklet values to calculate. All right. So all the methods method 1 to 5, the basis behind it is Hess's law. That means the energy does not differ if the pathway changes, as long as the starting and the ending materials, or starting and ending reactants and products are the same. Okay. So let's look at how we carry out each method. Okay. The main difficulty I feel is that after you learn there are 5 methods, sometimes you do not know when to use which method. Okay, so when do we use which method? If they refer us to data booklet, it's very clear, then we know which method to use. If not, if possible, whenever possible, try not to draw a Hess law cycle. Rather do manipulation of equation or do method 1, 2, 3 if it's possible. And really, if no choice, then we draw a Hess's law cycle. Okay, the reason is because drawing the Hess's law cycle is time consuming. All right, so I will start off with a manipulation equation first. You can see method manipulation equation. So let me show you manipulation equation. So I'm doing method 5, manipulation equation. So let's look at this question here. You can see that there's some equation. Equation 1, equation 2, and I'm supposed to calculate this. So I'm given some equations with the enthalpy value, and I am to calculate this, right? So I can draw a cycle, which is method 4, Hess law cycle, or I can just manipulate equations. So I will do manipulation of equations first. So what do we do when we manipulate equations? Very simple, okay? So remember the line in green is the equation that you're supposed to find. The one in green is supposed to find. So you cannot change the one in green. Okay? You can only change equation 1 or 2, but you can't change the one in green. So what you do is that you look for common terms. And when I say look for common terms, we try to avoid oxygen and water, if you can. Okay, look for common terms. And what happens after you find the common terms? So you check if they are on the same side. So you check if they are on the same side. If they are on the same side, let it be. If they are not on the same side, then you may have to flip your equation. Okay, so remember when I say flip your equation, you can flip anything, but not the green one. The green one is what you're supposed to find. So you cannot change the green one. So you check if they're on the same side. If they're not on the same side, flip the equation. All right, so if they are on the same side, then that's good. So we just let it be. If they are not on the same side, then what you have to do is you will have to flip the equation. Wait, let me. Okay, so check if they are on the same side. If not, flip the equation. So when you flip the equation, what happened to the delta H value? The delta H value changes sign. So it changes sign. So what do you mean by changing sign? So that means that if original was negative 148, after I flip the equation, it becomes positive 148. Okay, so flip the equation, the delta H value changes sign. Okay, from positive become negative, from negative become positive. Now, after you have arranged them to make sure they're on the same side, then the next thing that you will do is you check whether they are the same number of moles. So you check for same number of moles. So if they are not the same number of moles, then you multiply by a multiple. So if they are not the same number of moles, you multiply by a multiple. Okay? So for example, if mine was 2 moles and what was given was only 1 mole, then I multiply by 2 throughout to make it 2 moles. Okay, I'll show you in a while. Now, the first part, just to clarify, check if they are on the same side. Some students don't know what side I'm talking about. There are only 2 sides, reactant side or product side. Okay, check if they are on the same side. Okay, I'm going to demonstrate this using example 1. So remember the equation in green is what I'm supposed to solve. So let's look at equation 1 and my equation in green. Equation 1 and the one in green, what is the common term that I'm seeing in them? So let's say if I say, oh, common is copper. So then the thing is, we have to ask ourselves, we found our common term, check if they are on the same side. So in the one in green, copper is on the product, but the one on top, copper is on the reactant. So if they are not on the same side, so I have to flip the equation. So which equation am I flipping? I'm flipping equation 1. I cannot touch the one in green. Remember, I cannot touch the one in green. So I'm going to flip the equation 1. So equation 1 becomes like this. Cu2 plus 2Ag arrow Cu plus 2Ag plus. And what happened after I flip the equation? The delta H value changes sign. So original is negative 148. So now the delta H is positive 148. Positive 148. Okay? Then I'm done with equation 1. So now look for equation 2. What is common in equation 2 and the one in green? So I find zinc and zinc. So I found the common terms. I check if they are on the same side and both of them are on the reactant side. So if they are on the reactant side, both are correct, we leave it, let it be, right? Let it be. Then what will happen? So we don't have to do anything to it. Okay? So we can just leave it as it is, but for me, I will copy out because I want to show you something. Okay? So I will copy out the way it is, but I don't change anything. So I'm just copying it down. Okay, so that's not all. Remember, that's only step 1. Step 2, I have to check whether they are same number of moles. Correct? So just now was copper. Copper was 1 mole. My one equation in green is also 1 mole. So both are correct. So that's good. So remember, check for same side, check for same moles. All right. Now, then how about zinc? Zinc on same side, are they the same moles? Yeah, 1 mole each. That's good. So I have done step 1 and step 2. So what's next? So next it will be step 3. What do? I add them up. Add the delta H values together. So what's the rationale between adding the delta H values together? Because I am adding the equations together. All right. So what do I mean by adding the equations together? So I'm going to add up equation 1 and 2. So after I add up equation 1 and 2, I should get the equation in green. Let's check. So I'm going to add up equation 1 and 2. And I can see 2 silver cancel, 2 silver cancel. And I copy. Whatever was before the arrow is copper 2 plus zinc. Whatever is after the arrow, copper plus zinc 2 plus. All right. So is this the equation in green? Zinc plus copper 2 plus, copper 2 plus zinc 2 plus copper is exactly the equation in green, right? So by summing the two equations that I've manipulated, I get my equation in green. So the same will be for the delta H value, right? Since I sum the two equations, I will sum the delta H values that I've arranged. So the delta H of this reaction will therefore be 148 plus negative 363. Sum up the delta H values together, press your calculator, and you will get the delta H of this reaction. Okay, so this is how you do manipulating equations. So you get the value. Okay, so let's calculate the value. So I get negative 215 kilojoules per mole. Okay, there is this. Okay, I'll do one more time, manipulating equations using example 2. Okay, using example 2 again, this is the equation in green that I'm supposed to find. I'm supposed to find enthalpy change for this reaction. I'm given 2 other equations. So what do I do first? Check for common terms. So carbon, carbon, carbon and carbon, same side. So check for common terms, check for same side, check for same moles, right? So I've seen carbon and carbon, same side. So I don't have to flip equation, but I check for same moles. The one in green is 2 moles, whereas equation 1 is 1 mole. So what should I do to equation 1? I need to multiply by 2. So this becomes 2, 2, 2, and this becomes times 2. All right, so if I write out nicely the equation, it will be 2C plus 2O2 arrow 2CO2 equals to minus 394 times 2, right? Okay, that's equation 1, done. Equation 2, look for common terms. Okay, the common terms is CO, but it's on the wrong side. I cannot flip my green. I can only flip this equation. So I'm going to flip the equation. So they are on the wrong side. So the sign of delta H will change. But let's check whether they are the same moles. 2 moles and 2 moles. So just nice. No need to multiply. But I need to flip the equation. So after flipping, it will become 2CO2 arrow 2CO plus O2. So this value here will become positive 566 instead of negative. So flipping equation flips the delta H sign. So remember what we are doing, the rationale why we can add up these 2 values together to find the delta H of the reaction is because we are adding the equations together. Remember, just like this one, whether I start from C plus O to give you CO, or I take a bigger path, I go through B first, then B to D, then I sum these 2 together to give you H5. So that's the idea. So see, if I'm going directly, I'll get an enthalpy change value. If I sum up by these 2 steps, I should also get the same enthalpy change value. So let's cancel out common terms and see what we will get at the end. So I get 2C plus O2 give me 2CO. So is that what I want? Yeah, that's exactly what I wanted to find in the green. 2C plus O2 give you 2CO. Right, I add up the equations to get the green equation. So I should also add up the enthalpy change values to get the enthalpy change value for the green. So minus 394 times 2 plus 566. So my value will be minus 222. So what's the thing that we need to remember? Do not change the equation of the one that you're supposed to find. Look for common terms. Check whether they are the same side as the equation that you are trying to find. If they are on the wrong side, then you will flip the equation, flip the delta H. After you check the side, you need to check the moles. Make sure the number of moles are the same. If they are not the same, multiply by a multiple to make them the same. All right. And same for the delta H. The delta H will also be multiplied by the multiple. All right. At the end of the day, sum up all the delta H values. Okay. One last try. Now, in this last try, equations are not given, but they are given values here. So let me find another one. Okay. Let's look at example 4. Example 4, if I want to use manipulating equations to find out the enthalpy change. So let's read. The standard enthalpy change of combustion of carbon, hydrogen, and ethane are shown below. So this is for carbon, this is for hydrogen, this is for ethane. All of them shown below. The question says, use data, calculate enthalpy change of formation of ethane. So I need to come up with this equation in green. The equation in green is not given to me. I need to come up with the equation in green. How do I come up with it? So we go back to the definition of standard enthalpy change of formation. Okay, calculating enthalpy change of formation. So we need to understand what is enthalpy change of formation. Enthalpy change of formation means form one mole of the substance in its standard state from elements under standard conditions. All right, so it must be one mole. And it must be in the standard state. So some people don't know what is standard state. Standard state, that means the state that is found at room temperature. So example, what's the standard state of water? It's not solid, right? It's liquid. It's not gas also. It's not water vapor. It is liquid. So standard state is the state that the element is found or the substance is found in. So example, what's the standard state of diamond? You can't be telling me it's gas. It's solid because it's found as a solid. So this substance is formed from its respective elements. So for example, CO2 is formed from carbon and oxygen. Water is formed from the element hydrogen and oxygen. Okay, so I need to form from elements under standard conditions. And standard conditions here is not 22 points, it's not 0 degrees Celsius. Standard conditions here is usually room temperature, 298 Kelvin. 1 bar for gases, and 1 mole per dm cube for any solution. Okay, so it's usually 1 bar for gas pressure, 298 Kelvin. Okay, so the equation in green is formation of ethyl. I need to form 1 mole of ethyl. So C2H2 must be 1. And I must form from its elements. So the elements that exist are carbon and hydrogen gas. So I need to balance this. Ethyl at room temperature is in gas. So it's a substance in standard state. The standard state is gas. And hydrogen standard state is gas. Carbon is solid. Okay, balancing the equation, I need 2 carbon. 2C plus H2 give me C2H2. So this is enthalpy change of formation, where I form 1 mole of C2H2 from its elements, right? So this is the equation in green. Okay, it's the same as the previous question, just that in this question, the equation in green is not given. Okay, and my job is to find the delta H of this reaction. Okay, so again, now back to the 3 equation. So we check carbon, carbon, same element. But this is 2 moles. This one, same side, same on the reactant side, but 1 mole. So what should I do to the equation 1? So I take equation 1 times 2. So I get 2, 2, 2, and times 2. So if I want to rewrite it, it will be 2C plus 2O2 give me 2CO2. Then it gives you a minus 9394 times 2. Okay? Now, then hydrogen, same side, same moles. Same side, same moles, just leave it. Don't need to change anything. So, but I will just copy it again because I want to show you the summing up of the equation later. But you do not need to copy. Okay? You just leave it as it is. So, do not change the value, do not change the sign because it's the same side, same mole. So minus 286. I'm copying only. Next, C2H2. This is C2H2. This is C2H2. They are on the wrong side, but the same moles. So I need to flip equation 3 because I cannot change the one in green. So I flip the equation 3. So it will be 2CO2 plus water arrow C2H2 plus 5 over 2O2. So as I flip the equation, I must flip the sign. So it's 1 more C2O2, 1 more C2O2, now on the correct side. So what do I do to all these values? My job is very simple, add them up. Just like how I added all the equations together. If I add all the equations together, I will get cancel, 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 whatever that you can cancel, you will cancel. and then you write it out. So you get 2C plus H2 before the arrow, after the arrow, C2H2. So we can see that by going through this three pathway, I still can get C2H2. So therefore, the enthalpy change should be the sum of everything. So take a calculator and add them up. Minus 394 times 2 plus negative 286 plus 1301. Okay, and my answer is 227. So this is using manipulation of equation. Now, besides manipulating equation, what else can I do? So let's go back to this. So I've covered method 5, which is manipulating equation. So now what else am I going to do is I'm going to do the Hess's law cycle. Okay, but I'm not very keen to keep drawing Hess's law cycle whenever we can. Okay, so I'm going to do drawing Hess's law cycle using the equations. So it's the same thing. I have 3 equations and I need to draw a Hess's law cycle. Okay, so what I will do is that I take one of the equation, any one, okay, and write it out. Zinc plus Cu2 plus arrow zinc 2 plus Cu. And what is the value of this? I don't know. A question mark. I'm done. Okay, second, I'm going to try to connect some equations to it. So I can see copper, I see copper here, same, right? So the equation 1 is telling me from copper, draw an arrow out. So I see copper, I draw an arrow out. And what else must be with copper? Copper must be with Ag plus. I have copper and I have zinc, but I have no Ag plus. So I add in Ag plus. So this is before the arrow. After the arrow, I have supposed to have Cu2 plus 2Ag. So in other words, you can see my equation hiding here. Cu plus 2Ag, Cu plus 2Ag, arrow, Cu2 plus 2Ag, Cu2 plus 2Ag. So I'm hiding the equation here actually, and the value of this reaction is minus 148. Okay, so I'm done with this equation. Next, I'm going to add in the next equation. I put it in blue. So zinc plus 2Ag plus. I see a zinc here. So they say from zinc, draw an arrow out. From zinc, draw an arrow out. And what it should be with the zinc? 2Ag plus. I don't have Ag plus, so I add 2Ag plus. So I have zinc plus 2Ag plus, arrow. And what should I get? I should get zinc 2 plus 2Ag. I have 2Ag, but I have no zinc, so I add zinc here. So it looks very funny, but can you see I'm just hiding equation 2 here? How? This is the start of equation 2. And at the end, I have zinc 2 plus and 2Ag. So I have zinc 2 plus and 2Ag. So I'm hiding equation 2 here. And the value is minus 363. Okay, so now what I've created is a cycle, a loop. So how do you make use of the loop to solve? You set a starting point and you set an ending point. So if I'm going to say this is the start, and I'm going to say this is the end. So going this way is a way from start to end. Going this way is another way from start to end. So therefore, my equation is, this is equals to this. So minus 363 is equals to question mark plus minus 148. Summing the question mark and 148 together forms this part. So then rearrange your equation a bit. Question mark is equals to minus 363 plus 148. And you will find that it is exactly the same working as below. All right, both should give you the same answer. So you'll be able to find the enthalpy of the unknown. Okay, so Hess's law cycle means you need to draw one equation, any equation, and try to connect the rest in. The connecting, just look for common terms, follow that and see whether you're supposed to draw an arrow out from it or draw an arrow pointing to it. Okay, I will show you one more example. Let's look at this. So you can choose any equation. You do not need to start with the one in green. So if I don't want to start with the one in green, I'll start with equation 2, can or not? Can. I can start with equation 2. Okay? I can start with equation 2. But remember, just now we already have multiplied by 2 throughout. So, I mean, if we want, we can keep it or we can keep the original question. So I start with equation 2. 2CO plus O2 arrow 2CO2. Value is minus 566. Okay, done. So now I do equation 1. I try to connect equation 1 to this. I want to point to CO2. I see a CO2, but mine is 2CO2. Here is CO2, so I cannot really point to it. So what I have to do is I have to multiply by 2 through equation 1. I multiply equation 1 by 2. So now I have 2CO2, and this is 2CO2. And the question says draw an arrow pointing to 2CO2. So I follow. I draw an arrow pointing to 2CO2. Before the arrow is 2C, I have 2C and 2O2, right? Before the arrow, these are the items that is before the arrow, 2C and 2O2. So I have to write down 2C plus 2O2, right? So I'm hiding equation 1 here. This is the start, and this is the end. So in a way, I'm hiding it here. And the value here would be minus 394 times 2. Why times 2? Because I multiplied by 2 throughout, right? So I have to times 2. So this is one part, equation 1 done. So now the green one. Huh? So what is common with the green one? I have a CO, 2CO, 2CO. What am I supposed to do? I'm supposed to draw an arrow pointing to it. So I draw an arrow pointing to it. What is before the arrow? 2 carbon. What is before the arrow? Oxygen. I have oxygen actually. I have oxygen already. So what is the value? Don't know. I don't know what's the value. Okay. So I'm hiding the equation here. What I have is I have 2C plus some O2 will give you 2CO. All right. So if you want, you can double check whether your equations are balanced. How? So you take this part and this part. This is before the green arrow. This is after the green arrow, right? Before I have 2 carbon, 2 carbon. After, before I have 4 oxygen atoms. So 2 times 2, 2O plus 2O, so 4, balance. Okay, I can check like this. I can also check on the other side also. So let's say I check this side also. Before the orange arrow, I have 2 carbon, 2 carbon. Before I have 4 oxygen atom, so 2 times 2, 4. After also have 4. So the whole Hassel cycle is balanced already, right? So I need to define a start and an end. So you need to define a start and an end. So let's say if I define this as my start and I define this as my end. So this is one path. That is another path, right? So you can see this is one path. That's another path. It should be the same. Or sometimes you can see total clockwise is equals to total anti-clockwise. You can also use this, which is total clockwise is equals to total anti-clockwise. All right. But if you want start and end is easier, then you go start and end. So this path should equals to this path. So this path over here is minus 394 times 2. And it should be equal to question mark plus minus 566. So then you can solve your equation. You can solve your equation and make question mark on one side. So question mark will become minus 394 times 2 plus 566, which is what we are doing here. Can you see? It's the same outcome. All right, so you can practice drawing your Hess's law cycle on your own with this and see how it goes. So if you have this, then there are 4 equations. 3 equations will be triangle shape. So 3 equations will be like this type of triangle shape. Okay, but if there are 4 equations, like this, then likely it will be a square shape. Like this, 1, 2, 3, 4, 4 equations, so it will be a square shape. Okay, so what is the last equation that was missing? Was the equation that we wrote on our own for definition. If you remember, we wrote this equation on our own, which is 2C plus H2 to give me C2H2, and this is unknown. Okay, I'll do one last drawing if you need to. But I'm not encouraging you all to do drawing because it's such a waste of time when you can do algebraic method or you can do the manipulative equations and you can get results faster. Okay, but I'll just do one more drawing for people who likes to draw. So I'm going to draw equation 1, 2, 3 and the one in green. So I can start off with the equation 3 and just randomly start off with equation 3. I get C2H2 plus 5 over 2 oxygen, arrow to CO2 plus water. And the value is minus 1301. Okay, then I'm going to add in equation 2. How to add in equation 2? Equation 2 says point to water, arrow point to water. I see water, I draw an arrow point to water. And before the arrow, I have H2 plus half O2. And the value is minus 286. So I'm done with this. Next, let's look at equation 1. They say that, what else can I connect with equation 1? Oh, I have a CO2. I have CO2. Yeah, CO2. And they say draw an arrow to CO2. So this is CO2. I'm going to draw an arrow to CO2 then. And what is before the arrow? 2 carbon plus oxygen. We can balance the oxygen later, no problem. Okay, but I just put it down first. So in a way, I'm hiding the equation inside here. Can you see 2 carbon plus 2 oxygen, 2 carbon plus oxygen? Right, and then at the end, you have 2 CO2. I'm hiding this equation here, right? In a way. So later, then we balance the oxygen. If it's too many oxygen, we will balance later. So the value of this arrow is minus 394 times 2. Okay, I'm done with this also. So 1, 2, 3. Now the one in green. 2C plus H2 arrow C2H2. So I see C2H2. I'm supposed to draw an arrow to it. Before the arrow, I must have 2C. I have 2C. And before I have H2, I already have H2. So no need to add already. I already have 2C and H2, which is what is before. Right, I have what is before and I have what is after. So I'm hiding this equation here actually in the picture. Right, so what's the value of this arrow? What's the value on this arrow? I don't know. That's what I'm supposed to find. So I'll just put question mark. So I finished my cycle. Of course, you don't like my cycle, right? So let's double check and see whether it's balanced. So before the orange arrow, these are all before the orange arrow, right? And these are all after the orange arrow. So let's balance 2 carbon. I must have 5 oxygen. So now I have 2 times 2, 4 plus half, 5. Oh, correct. Then I balance the H. I have 2 hydrogen, balance. So before the green arrow is balanced. Before the blue arrow, this whole chunk is before the blue. This whole chunk is after the blue. So also balance. Okay, so let's balance the other side. This whole chunk is before the green arrow. And this is after the green arrow. So before I have 2 carbon, 2 hydrogen, 5 oxygen, balance. So everything is balanced already. Okay, so how do we draw it? If you like clockwise, anti-clockwise, so you will see that these two arrows are going clockwise, whereas these two are going anti-clockwise. If you cannot see clockwise, anti-clockwise, then you use another method, which is start and end. So let's make this the start. And make this the end. So I can go this way, I can go by this path. So going by this path, I need to sum up all this. These are all in this path, right? Or if not, I don't like this path, I can take a bigger path, which is sum up the green and red element. So I can see that sum green plus red equals to sum orange plus blue, right? Because there are two paths. So it will be question mark plus negative 1301. It must equals to the sum of these two, orange and blue, minus 286 plus minus 394 times 2. So rearrange, make question mark the subject, then you'll be able to find the enthalpy change of the reaction. Okay, so that's using Hess's law cycle. Now remember, whenever we can, we do not use Hess's law cycle. Okay, we try to use other method like manipulation or formula. So formula, we are going to use formula like HF and HC. Right, so whether we use HF or HC depends on what are the values that you are using. If you are using HC values, you will use this mathematical formula. If you are using HF values, then you will use this mathematical formula. Okay, so let's look at one question. Okay, I have this question here. The standard enthalpy change of formation of aluminium oxide and iron oxide are this. So what am I using? I am using HF. F for formation. Okay, enthalpy change of formation means delta HF. So I'm given delta HF of aluminium oxide is minus 1669 if I write out the question. Delta HF of iron 2 oxide is minus 822. That's what the question is saying. All right. Now, if you still remember what is formation, which we have seen earlier, formation is forming one mole of substance from its standard state, from its element, and the standard condition. So I'm forming one mole of something from its elements under standard condition. So if you understand that, then you will realize that the delta H formation of all elements is 0. Okay, why? Because formation is forming one mole of that thing from its element. Right? So example, delta HF of aluminium is 0 because I am forming aluminium from aluminium. I'm forming one mole of aluminium from the element aluminium. So there is actually no reaction. No reaction, of course, there's no change. Right? So many students will forget that delta H element is 0. You will not be able to find in the data booklet. So the delta HF values are in table 13 of the data booklet, but you will not be able to find elements inside. So that means in this question, aluminium delta HF is 0. And the same for iron. I cannot form iron from iron. If I form iron from iron, which is I'm forming one mole of the substance from its element iron, is no change. There's no reaction. So delta HF of iron is 0. So delta HF iron is 0. So what you are seeing here is that I am using formation data. All the data are formation and I'm using it to solve this reaction. So if you go back to the table, the mathematical formula will be for number 2. Formation, right, is reaction equals to product minus reactant. Can you remember this line? reaction is product minus reactant. So I'm going to cover this method now. Formation, the one that I'm using, formation, reaction of is equals to formation of product minus reactant. So delta H reaction is equals to product delta HF minus reactant delta HF. Right? So in this reaction, this is the reaction. This is the reaction. And this side is called the product. And this side is called the reactant. So I must take the product HF value, sum it up, minus the reactant HF value. So what is the product HF value? Al2O3 minus 1669. Other product, iron, 0. So no need to plus 0. So this is my product. Minus reactant, aluminum is 0. Iron 2O3, Fe2O3, minus 822. So product minus reactant value, which is minus 822. Take a calculator and calculate, that's all. Product values minus reactant values. So the product values are minus 1669. Minus of reactant value, which is minus become plus 822. So I'll get negative 847 kilojoules per mole. That's the enthalpy change of this reaction at the top. Okay? So when do we use this formula? We use this formula when we are looking at data. We are using data that's based on formation. And where can I find formation data? Either is given in the question or table 13. Formation data. Okay, so I will try one more question for formation to let you see. Let me give you formation. Okay, let's look at question 3. Determine formation of ethanoic acid given the following. So I know this, my job is to find the formation of this. I don't know how much. Okay, I don't know. Formation of oxygen is also not given. Formation of oxygen is not given because you cannot form oxygen from oxygen. There's no reaction. So it's actually 0 because enthalpy change of formation of an element is 0. Okay, so 0. Formation of CO2 is given 394 kilojoules per mole. But now I'm not having 1 mole. I'm having 2 moles. It's 392 per mole. So I'm having 2 moles, so I need to times 2 later. All right, formation of water is given as minus 286, but again is per mole. I have 2 moles, so I need to multiply by 2 later. All right, so can you still remember what's the mathematical formula? Delta H reaction is equals to sum of the delta H formation products minus sum of the delta H formation reactants. So this is the equation. This side is called product. This side is called reactant. Reaction is given. So I'll sub in the value minus 876 is reaction equals to product. Product is 2 carbon dioxide. Each carbon dioxide is minus 394, right? So I need to 2 times minus 394. That is for carbon dioxide. Product also has water. So I need to sum up the water also. And there are 2 water. Every water is minus 286. So plus 2 times minus 286. And that's my product. Product minus reactant. Reactant is this one, which we do not know what is it. So we call it X. Let's call it X. So minus X plus oxygen, which is 0. So it is X plus 0. So it's X. So now I have an equation. whereby I only do not know x. So if I rearrange, I'll get minus 876 equals to minus 394 times 2. Let's work it out. Minus 394 times 2. So I'll get minus 788. Then minus 286 times 2. I'll get minus 572. So minus 788 minus 572 is the sum of the product, right? So I need to sum them up. So minus 788 minus 572. Sum them up, I'll get minus 1360. So I put minus 1360. Okay, that is my product minus x. So if I bring x on one side, x will equals to minus 1360 plus 876. So I'll get minus 1360 plus 876. I get minus 484. So the enthalpy change of formation of ethanoic acid at the question at the top is 484. All right, that one is if you are using formation data. Now, next, we are going to look at using other data. So remember, we have done the method using formation data. So let's see what else can we use. Okay, this question is also formation. All right, how do I know this question is formation? The question never tell me it's formation. But if you look carefully the equation, remember what is formation? Formation is forming one mole from its elements. So I'm forming one mole of Cr2O3 from the element chromium, from the element oxygen. So therefore, delta H1 is actually a formation data. Okay, second, let's look at the second one. I am forming one mole of CO, forming from the element carbon, the element oxygen. So I am forming one mole of carbon monoxide by the elements. So this delta H2 is actually formation. So I am given formation data to find enthalpy change of a reaction. Right? So let's look at this reaction. Under the product side, I have chromium and CO. But I don't have delta H chromium. This delta H1130, this delta HF1130 is the delta HF of Cr2O3. Okay, this delta HF of minus 111 is the formation of CO. Right, so I have Cr2O3 formation, I have CO formation. So I have this, I have this. I have these two formation value. But these two I do not have. But if you look at it carefully, these are elements. You cannot form chromium from chromium. You cannot form carbon from carbon in a way. So therefore, the delta HF of carbon is 0. Delta HF of chromium is 0. So in a way, I have everybody's delta HF value. So if I know all the delta HF value, then delta H reaction will be sum of delta HF products minus sum of delta HF reactant. Right? So the products are chromium and CO. So I'll sum up the product first. Chromium is 0. So 2 times 0 is still 0. Carbon monoxide is minus 111 kilojoules per mole. But I am having 3 moles. So it will be minus 111 times 3. That's the product. Minus the reactant. Sum of the reactant is chromium, Cr2O3, and carbon, Cr2O3 and carbon. Enthalpy change of carbon formation is 0. So only left is Cr2O3 minus 1130. So the answer will be minus 333 plus 1130. Take your calculator and press, and you'll be able to get enthalpy change of the reaction. And I'm using formation data. All right, next. So I've already done 3 methods, formation data, So I'm going to use combustion data now. So combustion data is like formation data. The only difference is you are using different data. You are using combustion values, and combustion values are in table 14. So you go to table 14, you see all these values. So you are using all this data to calculate. And when you are using combustion data, the mathematical formula is different. It is reactant minus product. Okay, is reactant minus product. Now, and what are the delta HC values? They are zero. Just now, there are delta HF, they are zero, they are elements. So is there delta HC for element zero? No. Delta HC of elements like carbon, sulfur, you can see they are not zero. Delta HC of elements are not zero. Then delta HC of elements are what? Is there any delta HC values equals to zero? Yes. Delta HC of oxygen is zero. Delta HC of water is zero. Okay, so then the question is, what is HC? What is HC? So HC is the amount of enthalpy change when 1 mole of that substance is burned in excess oxygen. So if I burn 1 mole of carbon in excess oxygen, I'll get CO2. So there is a reaction. And because there is a reaction, there'll be enthalpy change. Can I burn hydrogen? Can. If I burn 1 mole of hydrogen in excess oxygen, then I'll get water. So there is a reaction. So there will be an enthalpy change for this burning. This burning is called combustion. So there will be an enthalpy change for the combustion. Okay, is it only elements that I can burn? No, I can burn anything. So I can burn alkanes. I can burn alkenes. Right, I can burn. Burn in excess oxygen, then I will get whatever is left after you burn. So CO2 and water. Then I balance the equation, right? CO2 and water. So I'm not balancing it, but I'm just trying to tell you they can all be burned. It's because they can all be combust. So therefore, they have a combustion value. Okay, they have combustion value because they can be combust. So are there things which have no combustion value? Yeah, there are things which have no combustion value, which is oxygen and water. You cannot burn oxygen in oxygen. Oxygen will not react with itself. So you cannot burn oxygen in oxygen, right? So therefore, there is no reaction. No reaction, so enthalpy change is zero. Can you burn water? You can't burn water. Water is used to put out fire. How can you burn water? So you cannot burn water. There's no such thing as burning water, right? You cannot burn water, then there's no reaction. No reaction, the enthalpy change of combustion of water is zero. Okay? So basically, you can't burn oxygen, you can't burn water. Most of other things, all you can burn, all you can combust. So therefore, they should have a value. All right? So if I'm using method 3, then I'll be using values from table 14, and my formula will be reactants minus product. So let me show you an example. Example will be this. Remember this question? Yep. Okay, remember this question here? They say that the enthalpy change of combustion are shown. So all these values that we are seeing here are all combustion. It's actually delta HC. HC of what? HC of carbon. Delta HC. HC of what? HC of hydrogen. Delta HC. HC of what? Of C2H2. So I have all the delta HC. And I'm supposed to use it to calculate the formation of ethyne. So what is the equation? 2C plus H2 to give you C2H2. So let me copy it down. 2C plus H2 give you C2H2. So the question is asking me, can you find this delta H reaction? Can I find this? And This happened to be a formation, but this can be anything. But this is just a reaction. I'm going to find this reaction using combustion data. So remember, it's the data that I'm using that determine the mathematical formula. I'm using combustion data. So if I'm using combustion data, then the mathematical formula will be sum of HC reactants minus sum of HC products. Okay, if I'm using combustion data, then this will be the formula. So the reactants are carbon and hydrogen. The products is C2H2. So if I'm going to sub in the equation, it will look like this. So delta H reaction is equals to reactant is 2 carbon. Per carbon is minus 394. Per carbon is minus 394. So minus 394 times 2. Some more? Under the reactant, I have H2. So add in H2. So reactant is not just C plus also H2. So H2 is 286 plus negative 286. So all these are my reactant. And I'm going to use my reactant minus the product. Product is C2H2, 1 mole. 1 mole of C2H2 is minus 1301. So minus negative 1301. Minus minus become plus. Okay, take a calculator, press the calculator, and you get the answer. So you don't need to draw complex cycles like this. And you also can no need to do algebraic method if you want to use the formula method. Okay, I will do one more, combustion. Okay, this is a question on combustion. Because they give you the subscript C. It's very clear, they give you the subscript C. So calculate enthalpy change of the reaction given for the data. So this is the reaction. And this is my HC, HC, HC. So there are 3 reactants and I have 3 substances, 1, 2, 3 in the equation. I have 3 HC. Right? So delta H reaction is equals to reactant minus product because I'm using HC. So reactant means these 2. Let's find out the reactant. Reactant is minus 1411 plus hydrogen 1 mole minus 286. So these are my reactant. Reactant sum up minus the product. Product is minus 1561. Press the calculator, you get the answer. All right, so the formula is reactant minus product if I'm using combustion data. All right, last method already. Last method. So the last method to find enthalpy change by calculation without experiment is to use bond energy. Bond energy is what you have learned in year 4. Okay, whereby you calculate how much energy to break every bond and how much energy is given out by every bond form, and the net change is the energy of the reaction. So therefore, the formula will be bond energy reactance, which means last time your bond breaking, minus bond energy product, which is your bond forming. So bond breaking minus bond forming. So bond energy method, we will use table 12 of the data booklet. So I will show you data booklet first. So this is table 12 of the data booklet. Now, one thing about bond energy is that these values in table 12, most of them are average values. What do you mean by average values? That means they look at the same bond in many different compounds and they take the values and average it. So, for example, a CH bond. They may have taken the CH bond from an alkanes, from alkene, from alcohol, from acid, from all other things, alkyne, everything that has CH bond, and they average it. So, in a way, it's not very accurate already because you're averaging it. It's not really the real value of the substance you're looking at. So, this averaging brings about some errors. Okay, so take note whenever you're using the data booklet values, some of the values are average bond energy, and that could be one source of the difference compared to other method of calculation. So the averaging does not reflect the actual environment of the CH bond in the compound that you're looking at. However, there are some bond energy in the data booklet. They are not average. They are the real ones. And which are the real ones? You'll find that the real ones are usually the bond energy of diatomic molecules. Example, fluorine, fluorine, chlorine, chlorine, H, H, Br, Br, I. Okay, why? Because there's no other substances in the world that has a HH bond besides hydrogen. If there's more than one substance that has this bond, then we can average. But there's no other substances in the world that has this bond. So say for FF, ClCl, there are no other substances in the world that has FF, ClCl bond. So there's nothing to average with it. So these are the actual number. These are the actual bond energy. All right. So the bond energy in the data booklet mostly are average bond energy, except for a few, which is the real energy. So what in the world is bond energy? Bond energy is the energy to break one mole of covalent bond in gaseous molecule. It is for covalent bond only. So there's no such thing as ionic bond, NaCl. Is there a bond energy? There's no bond energy. It's for covalent. Okay? So it's the energy needed to break one mole of covalent bond, and it must be gaseous. So if I have H2O in liquid state, can I say that's the bond energy? No, because bond energy must be gaseous. So it's only when it's H2O gas, which is steam, then I can say that there's a bond energy. All right. So ionic, no bond energy. Other states, no bond energy, because by right, it should be gaseous. So you'll find that bond energy calculation is usually for a reaction that only involves gases. I repeat that. So bond energy calculation method is only used for reactions that involve gases. Okay, if it's not gases, if some are liquid, some are gases, and you are asked to use bond energy to calculate, then of course the result will be off. Okay, so bond energy is the energy to break one mole of gaseous covalent bond. So example, if I break HH bond, I'm breaking one mole of bond. After I break a HH bond, the amount of energy needed to break it. After breaking, what do I get? I get 2 hydrogen atoms. This is a molecule. So I break a molecule, I get 2 atoms. Right? So that's the bond energy. It's found in data booklet section 12. All right. So what about the bond energy that you need to take note is that you use it for equations which are all gases, and also there is some assumptions that we are using. The assumption is that we know the values, some of them are average. So they are not very accurate, but we are assuming they are. Okay, why are they not as accurate? Because it does not reflect the actual environment of the substance. Okay, it's not the actual bond in the substance. It's the average after you factor a wide range of compounds which has this bond. All right, next, bond energy is for covalent. You cannot use it for ionic, cannot use it for metallic. All right, next, bond energy is for gaseous. So you cannot use it for liquid. If you use it for liquid, then the answer will be different. Right? Because vaporization is not there. So let me look at some questions on bond energy. So the bond energy of this and this are so much. The enthalpy change of the reaction is so much. What is the bond energy of FF? So what do we see first? This is the reaction. And what else? We are seeing everything gases. That's why we can use bond energy, right? So the formula is delta H reaction is sum of bond energy reactants minus sum of bond energy of product. So reaction is given as minus 268. Reactant. So you were to draw out. Last time you learned how to draw it out and then you can see. So now I do not have one HH bond. I have half a HH bond, right? So I need to multiply by half. So one HH bond is 436. So I need half times 436. That is my reactant. And I need to half FF. So I don't know what is FF. Right, I let FF be X. So I plus half X. This is my reactant. Minus product is HF. HF is 567. 567. Okay, so then with that, we'll be able to calculate minus 268 equals to half of 436. So it's 218 plus X, half X minus 567. So we make X on one side, so minus 268 minus 218 plus 567 is equals to half X. Then you can solve X. So minus 268 minus 218 plus 567, and that is half X, so I times 2. So 162 kilojoules per mole is X. Okay, so I'll try one more. All right, now this is the reaction. So usually in the past, what your teacher will teach you to do is you ask you to draw out so that you can count how many CH bonds, how many CC bonds are there. So if you draw out, then you can count the bonds. So what you will do is you will first draw out the structure, and then you see they are all gases, right? So we have, these are my reactants, these are my products. So I have one FF bond, one CC double bond, 4 CH bond. I have one CC single bond, 2 CF bond, 4 CH bond. So if you hear me, there are 4 CH bond, there are 4 CH bonds. So they all cancel out each other already. So we don't need to care about the CH. So what we will have to care about will be over here, under the reactants, the bond in the reactants will be FF158 plus 1 CC double bond, 615. So FF plus CC double bond. So let's work it out. It will be 158 plus 615. Separate out your working so that if you make a mistake, you will get working marks. So I bond in my reactors, I work out. Bond in my products, our CH all cancel out already, so we don't need to care about CH. It will be just 1 CC single bond, 348 plus 2 CF single bond, 441 plus 441. Okay, so or you can use 441 times 2 plus 348. So you get 1230. So the formula is reactant minus product. So delta H of the reaction will be 773 minus 1230. Reactant minus product. 773 minus 1230. I get negative 457 kilojoules per mole. So the enthalpy change of this reaction, is minus 457 kilojoules per mole. All right, so these are the few methods to find enthalpy change of covalent compound that is not experimental based. So experiment based will be calorimetry, which will be this part here, the earlier part of the notes. All right, but the enthalpy change calculation by no experiment will be the 5 methods. So now I already covered the last method, which is bond energy. Okay, so let's do a quick recap. The 5 methods are manipulation of equation, Hess law cycle, using formation data, using combustion data, and using bond energy. Okay, so these are the 5 ways to calculate enthalpy change without an experiment for covalent compound. Okay, that's all. Okay, that will be all for this holiday learning. Bye bye.